Great. Well, thanks for having me. Um, I have been involved with TLA Plus from an educator's perspective. So, a very brief background here. So, I've been basically in academic research and education for over 30 years. Been at Loyola Chicago since 92, so my first job, and I'm still there. So, something's working out there. And I'm originally from a programming languages research background, branched out a little bit more into software frameworks, architectures, a little bit of high performance computing. And recently, so 3 years ago, my colleague who's currently chairperson asked me, oh, we've had this formal methods course in our course catalog for, I don't know how long, like 10 or more years. And we've never actually had the staff to offer it. So I said, well, it's time we offer this course, so why don't you do it? So I said, well, sounds like a great learning opportunity. And then I asked him, do you have an idea? Like, I know there are a bunch of model checkers out there. Do you have any idea which one I should use? And he said, why don't you look at TLA Plus? So that's how this started. And let's see where we go from here. I also wanted to give you a little bit of a broader context. I know the talk is really about the Python notebook, but I think that won't take that much time. But really, my main goal is to connect with the community in such a way that we can partner and make formal methods, especially model checking using TLA plus, available to a broader audience, not just elite universities, but let's say more broadly in academia, in such a way that we can get more of a multiplier effect to help maybe grow the talent pool. So let's see, what are some key elements here? So it's really, from our point of view, about the examples. So the examples have to be engaging and fun. And fortunately, there are collections of examples out there. I'm going to point one out later. And the idea is just to convey to students that there's value in thinking about requirements in this kind of formal way, not just in terms of these lengthy requirements docs that then you can't really work with them or do anything specific with them, but something that's really tool-based and engaging. So then we start with puzzles, like the Die Hard river crossing and those kinds of things. And then we go to um, things that are familiar, but where there could be more of a safety and liveness requirement as a very important part of those kinds of examples. So, but the overall goal is basically this last item here, to attempt to broaden adoption of formal methods in academia. And I don't need to spend much time talking about these things. So some of these materials are from a talk I gave at the Frontiers in Education Conference, the IEEE Education Engineering Conference. And we also have basically a version of the conference paper in IEEE Computer Magazine. So it's going to get some visibility just being in the magazine, which is read by a broader audience. So this is what we found when we started looking at the extent of adoption of formal methods, especially model checking and in education. So there are very good continuing efforts out there. And there's this nice formal methods education database, uh, which is searchable in various ways. You could search by tool used, by the kinds of methods and concepts used, etc. So there's definitely some very good work going on. The key challenges, and we've referenced the key studies that we've found in our papers. So these are some of the main challenges, basically. So insufficient mathematical background in students, and we have started thinking about a way to address that more directly. Um, Lack of engaging case studies and tool documentation, I think that is actually getting better. right? So we started using alloy, and I think there's good material out there, and as well as TLA plus, where there's a nice collection of examples, and there's some nice tutorials like Hillel Wayne's materials, etc. So um, the other issue is students' learning styles tend to be maybe more um, based on experimentation, discovery, focusing on solutions. And I think that, that can definitely be addressed also. So I think in general, things look promising, and I'm just going to share an example that we have been using. And again, my hope is to get some feedback at some point, to kind of engage with the community and build, let's say, start an ongoing conversation. So this is our institutional context. So the point is, so we recently became a Research 1 institution in the Carnegie classification, but it's mostly because the criteria got lowered a little bit. So all of a sudden, a bunch of universities got added to R1. How many here are in academia, actually? Okay, so, and this includes classroom teaching for all of you. Okay, cool. Yeah, so I'd love to compare notes with all of you as well. So my point is, so we're a kind of mid-sized national non-elite university, and our demographics also represents this. So we have a lot of students from underrepresented groups, including minorities, including families where the student that we get is the first college goer in the family. So this is also an important demographic we keep an eye on. And we're in an urban setting, so we're actually in the city of Chicago. And department is mid-size and growing. We recently added a PhD program just 2 years ago. That was a very hard case we had to make over several decades until that was finally approved after several chairpersons' hard work in making the case. So we're generally also research active as a department, so we have support from various federal agencies as well as industry. Okay, so the curricular context, and this is where it gets to the part about the mathematical preparation, where we're starting to see an opportunity to improve a pipeline. So we have a typical ACM-based curriculum where we have an introduction to programming, using imperative slash object-oriented. Then we have a data structures 1 course, which is linear data structures. We also have the course historically known as CS7, which is nonlinear data structures. And so at dinner, this came up yesterday, like, we really require the nonlinear one for them to get started. Like, where's the sweet spot? Do we get them started earlier in formal methods, even though they might not have the full understanding of what goes on under the hood? Or do we wait and then risk getting them started later, or maybe having a situation where they might not have time to fit the course into their own course of study? So that's an ongoing discussion we're having in the department as well. And then really the key course that uh, constitutes the pipeline into our current formal methods course is this discrete math, discrete structures course. So this is where we believe there is a good opportunity to fully set the tracks. Because previously, so this course has been really mostly an orphan, where they say, okay, you have to have this because you're going to need it throughout your curriculum. But there isn't a clear, let's say, um, pathway into more advanced courses that are directly tied to the discrete structures course. So what we're trying to do there, and my colleague who teaches these sections has gotten excited about it. So we're starting to sensitize students, and these are often, let's say, first year or early second year students in the discrete math course. So we're going to have curricular content where they get some initial exposure to automated theorem proving using Lean, just so they can see, oh, these tools can make things easier and more exciting at the same time, right? So that's the idea. And then the message at the end of the semester is, of course, if you're excited about this, then make sure you have the third or fourth year formal methods courses, which is the one that I've been teaching. So for the third time this semester, course on your radar as basically the next step, even though there are gaps in between in terms of the timeline, but at least having a clear direction, we believe will help. Um, make the discrete structures course more interesting, as well as improve the situation regarding the mathematical background required to get the full experience in the subsequent formal methods course. Okay. Um, so this is how we are tying the modules, the learning modules in the formal methods course, not only to the discrete structures course, but also to the programming courses. So because they come out of the programming courses knowing some automated unit testing, but it's very basic. It's what we call ad hoc or example-based unit testing, meaning you just write you come up with a bunch of test cases, and you're probably familiar with a method that provides a little bit of guidance, like what your test cases should be based on. And this is often called the zombies method. Does that sound familiar? Zero, one, many, right? So you capture those various boundaries, exceptions, interfaces, that type of thing. So the zombies acronym captures that. So we introduce that, and then it's kind of a natural transition to say, well, we can make it more concise by using table-based testing, and then we can make it align with the specification by going to properties-based testing. And there we say, okay, well, you got to remember those quantifiers from the discrete math course, etc. And we grounded. We can say, well, to be really certain about correctness, you'd have to do exhaustive testing, so the property-based testing can achieve that. And to show that something's incorrect, all you need is one counterexample. So that's where we tie it to, for example, the existential quantifier. So we try to ground everything in the previous courses they had. So we do JQuick-based, property-based testing, both stateless and stateful. And we recently inserted a module on alloy to introduce them a little bit to relational logic so they can understand consistencies or inconsistencies in their structural models. And then we pretty much spend the second half of the semester on on behavioral model checking using TLA plus. So that's where the real fun starts. I got to improve a little bit on my alloy module. It's just a thing I just added recently. So, but the TLA plus, this was my third time doing it in the course. And this is the familiar example. So I don't think this is in the examples repository, and maybe we can contribute, if there's an interest in this being there, I'll be very happy to, to pair with you on that. But right now it's just on it's in GitHub, obviously, right? So, but the point is, this is familiar and engaging. Everybody knows it. It's like a globally known kind of, but safety critical appliance, right? So there are these safety characteristics, right? So if the door is open, the radiation must be off. And if the radiation is on, the door must be closed. Well, these are obviously equivalent. But then there's also an opportunity to talk about liveness, right? So if it's running, it needs to come to an end at some point, right? So there's this duty cycle consideration also. So we try to use very hands-on, very real-world grounded use cases here. So then we introduce the actual notation, etc. So I'm going to go through this relatively quickly, but they can see that even the initial state doesn't have to be unique, for example. Then there's a very simple kind of choice among these next actions. And let's see. So the interesting one is probably the tick, and that's the one I don't have here. Um, and then we explain what the model checker does and how it can report violations of invariants as well as temporal properties. And really the main point that we try to convey is that the model checker doesn't have a bias where a human developer would say, oh, that's not likely to occur, I don't have to worry about it. And that's how a lot of bugs arise like that, right? So it's going to just, in an unbiased way, explore the entire state space. So they can very quickly understand the value in this, so like this is the kind of thing where I ask them in class, like, what do you, what's wrong here? And they participate. So it's like a kind of Socratic method, asking them questions and then trying to get them to contribute. So obviously, I mean, this violates the door safety invariant, right? So this is the case where it's running and then you open the door. And then we fix that, like we patch that in the model, right? And then we say, oh, it should be safe now, right? We patched it. Then we run it again. And then we got the counterpart, which is where it's not running and the door is open and then we hit start. We got to patch that as well, right? So in other words, it's so easy to overlook um, potential safety violations. And that's really why we need proper tools for this. So proper modeling. Thank you so much. So same thing here, just a different trace leading to this safety violation. So now this one, right? What does this violate? That's right. And this is where it gets more subtle, right? So here's a liveness property, right? So whenever radiation is on, it has to lead to radiation being off at some point. And so, I mean, you're the expert, so this requires a more advanced technique, which is, that's right, exactly. So we try to make these connections because fairness, I mean, it took me several iterations to wrap my head around it, and weak fairness is sufficient here. So I was using Hillel's notes and just rereading them over and over. And yeah, so I think we've got a kind of a convincing case why this is important. So here's a list of these fun examples. I mentioned some of these earlier. What we love about TLA Plus is how we can start with a very abstract model and then gradually make it more detailed. For example, for the elevator, um, we can ignore a lot of the details, but still have a meaningful simulation. So for example, we can ignore, oh, it has inner doors, outer doors. We have to be careful that the inner doors don't open without the elevator being at a floor and all those kinds of things. But that's not necessary for an initial model. The initial model can just be, well, if someone requests the elevator will eventually go there and pick up that request or serve that request. So, and that's the type of project that we assign them so they can think, and then the more advanced features or characteristics, we can, for example, assign those as extra credit, or we can require the graduate students to tackle those and the undergrads just do a more basic version. And then toward the end, so we do these classic concurrency examples. So for example, several concurrent tasks, each of which performs n increments of a shared variable. And it's the kind of thing where the lowest possible value of the shared variable, it's actually really it's unintuitive. So they're supposed to find a formula in terms of the number of concurrent activities and k, and then the number of repetitions n each activity performs. And then they will find an interesting result. And the source for a lot of these, so I did email you this, So this is a 20-year-old course at Aarhus on embedded systems verification, ESV, and their tool is called UPAL. So I'm not sure how widely this is still used, right? But I think it was mostly for teaching, and it also supports, I think, real-time modeling. But it's a rich source of examples. It's got almost, I think, almost 30 examples, and it's got all of these, the diehard vending machine, several iterations of a vending machine, and then the concurrent increment. I used their version for this. So there's one that's called How Low Can You Go, or How High Can You? So that is pretty much the course. And I think now we can kind of look at ways to run the model checker in more or less convenient ways, right? So the typical way is the toolbox. I'm not sure how widely used the toolbox is compared to, let's say, the VS Code extension, but I've only initially used the toolbox because I wasn't clear on what the configuration file syntax was. But for my own work, I use either a local VS Code instance, or in GitHub code spaces. Works amazingly well. You just fire it up. And I don't remember now whether the fonts work correctly. I think they have improved, but if you use the conceal extension, you get the very nice where these combined symbols show up as proper mathematical symbols, and it's actually really nice the way it looks. And then we had this idea, well, can we do this? So basically the code spaces is the third bullet here, right? So that's zero install. But it requires certain knowledge. And then we said, what about if we try to do this in a Python notebook where there's a truly zero install? And then if anyone, I gotta move this out of the way. So you could, in theory, pull up the notebook now. So the idea is that you can experiment instantly, and for the benefits of student engagement, making it easy to share and reproduce, making it easy for the educator to maintain, etc. And there's still a few things we need. So the pretty printing is we for now we do it manually, because if you go to a collab, it's not going to have a full LaTeX environment, for example. So it's just, you would have to use a local environment, and that would kind of defeat the purpose. So I am going to spare you the pain of a full live demo, because some of the steps take a minute or two, like the Java, like a modern Java install, using SDK man or that type of stuff. It just takes a little while. But basically, if you pull up this notebook, it shows the various installation commands required to set up the TLA model checking and simulation environment. So we just download the release, just the jar, which is all we need. Then we create these tiny scripts, right? So this next step here is just to verify that we're running a version of TLC. And then we can use write file to write our own little script. So we're kind of bringing up the scaffolding and everything. And then, for example, we can directly download our source from GitHub, so we don't have a double entry problem. We just maintain it in the repo. And then I'll just show very briefly the three key things we can do. So we can obviously experiment with multiple configuration settings, like saying which properties and invariants we're actually checking, and which settings we make for the model to actually satisfy those. Whether it implements the required door safety, or whether it's the basic model that just lets you do whatever you want, the unsafe model. So Now we can run our little script and, for example, it will show us a trace. So this is actual text, so this is not the live output. But then the other things we can do is, this does look like the actual output. So we have another tiny script for simulating, and we can look at the traces. So here's, for example, a trace we can look at. And then finally, we can actually run stuff in the REPL. So we had to do a little bit of glue code in Python to support cells that allow us, so that define this directive. So we call it %% TLA REPL, and it supports single expressions or multiple expressions in a row, like this. And then you can just kind of teach a few things like this. Finally, so that, like I said, the pretty printer, it requires a tiny LaTeX boilerplate wrapper, and it works uh, if you have a proper LaTeX environment. But here we're just kind of uploading the PDF. I think we're uploading it as an SVG. Yeah, here. And we're doing that manually, just to show that it's possible in principle. So this is basically the notebook, and we give students, the link to the notebook as one possible way to get started. But then we do move them to code spaces or local VS Code. They are familiar with VS Code usually. So to conclude, then I think I have 0 minutes left. So there are evaluation results, but really the main point is to focus on this integration. I have to go back to the slideshow, to focus on this integration between the discrete structures course and the subsequent formal methods course. But then beyond this, we just came up with a plan to take an approach that doesn't require rolling out a separate dedicated formal methods course, because for many colleges, this is actually a hard thing to do, to modify the major and introduce a whole new course. So the approach is to have smaller modules that they could fit into other courses. So there could be maybe a 2 to 3 week introductory module on model checking, and they could fit that maybe into an existing software engineering course. So that is our hope, and it's not our idea, this idea of infusing the curriculum by spreading modules throughout different courses. So we're adopting this from the CS in Parallel initiative, but the hope is that that will lower the adoption curve. Okay, so I am hopeful that we can stay in touch. I'm very interested in your thoughts and feedback. And this is just a link to, I think, again, the notebook, but you should be able to find me through LinkedIn or my email address. Right? So thank you so much.